Hello, future doctor. Tis me again, Alex. Welcome to your high-yield science lesson on amino acid electrophoresis. You might notice as we go through this lesson that there are shorter ways to go about doing things. And the reason we really dig deep here is because everything about amino acids is fair game on the MCAT. I mean, their categories, properties, polarity, everything down to their exact structure. And not only that, but they're versatile too, so you'll see them show up on your chem-phys and biochem sections of the MCAT. Better be actually familiar with them, and that's exactly what this lesson is for. Speaking of, after this lesson you'll be able to describe how the pH affects the base to acid ratio of a functional group, and you'll also be able to determine the net charge of an amino acid at any given pH. Take a few seconds to read this question stem. Here, we're given 3 amino acids, their functional groups pKa's, and the pH of our gel. What do we need to determine to figure out where amino acids are going to migrate? We need to figure out their charges at that particular pH. And of course, we could do this very quickly here. That's to say, figure out the pI, how it relates to the pH, and boom, we're done. But the neat thing here is that we can take a little detour and actually bypass finding the pI to answer this question. We can really take this opportunity to understand the relationships between a few variables. How do pKa's relate to isoelectric point? And how can the charge be inferred from the relationship between pI and pH? And I really use the word understand over the word know, because if you understand what gives rise to a particular relationship, then you're that much more likely to remember it until test day. Let's use the simplest amino acid, glycine, as our vessel to understand some of these relationships. We're told glycine's isoelectric point is around 6. Before we move any further, what do we know about an amino acid's overall charge when the pH is equal to its isoelectric point? That's when you will find the amino acid in its deuterion form. When the pH is equal to the pI, the amino acid's net charge must be 0. Technically, because an amino acid's pI can always be calculated from its group's pKa's, we should be able to see that glycine will have a neutral charge at a pH of 6 simply by finding the base to acid ratios of its two functional groups at that pH of 6. So let's find out what these ratios are. We have our two Henderson-Hasselbalch equations set up for our two functional groups. And let's take some time to appreciate what the Henderson-Hasselbalch equation tells us. It's basically saying, hey, I feel you. It's hard to tell how many molecules carrying a functional group are going to be protonated versus deprotonated in a particular solution. So if you just let me know the pH of the solution you're looking at and the pK of the functional group, I'll tell you how many molecules carrying the functional group will be protonated versus deprotonated. In other words, their acidic or basic form. We just have to do a little bit of plug and chug. Let's start with our carboxyl group. The pH of the solution is given in the question prompt, and that's equal to 6. Next, the pK refers to the pK of the carboxyl group, and that's information we need to retrieve from the table in our question stem. That's equal to 2.34, and then we can load up the rest of our equation. Nobody likes to deal with decimals, so let's simplify our 2.34 to the closest whole number, 2. If we further simplify, we see that 4 must equal the log of the base to acid ratio. What must that ratio equal to then? That ratio must be equal to 10, since that's the base of our log, raised to the power of 4. From there we can conclude that we have, at a pH of 6, 10,000 times more carboxylate ions than carboxylic acids. In other words, we have 10,000 times more base than acid. Based on these calculations, what's the general relationship we can extract in terms of the base to acid ratio when the pH is greater than the pK? Well, as we saw here, our pH was 6 and our pK was 2.34, and we ended up with a whole lot more base than acid. So when the pH is greater than the pKa, the base is favored. Okay, wonderful. Now that we've established this, I have a trick for you guys to remember your Henderson-Hasselbalch equation. But before that, let me ask you, what is true when the pH of a solution is equal to the pK of any functional group? We would have equal amounts of that functional group in acidic form and in basic form. And what happens to the proton concentration as the pH rises? It becomes lower. And protons are positive charges, so here's what I like to think. When pH is equal to pK, I have equal amounts of base and acid. If I make the pH higher, I'm removing positive charges necessary for that equilibrium, so I'm favoring the base. And you see that it works nicely also when you look at the Henderson-Hasselbalch equation. If you ever forget whether the acid or the base goes at the numerator, you can think, hey, more base than acid should give me a higher pH than pK, so the base must be at the numerator. We can apply the very same plug and check technique when we're looking at our amino group. The pH of our solution is still 6. The pK is going to be much more basic at 9.60. Again, that's the pK of the amino group based on the question stems table. And we have the rest of our Henderson-Hasselbalch equation. Again, 9.60 isn't too pretty to deal with, so let's change that to 10. And we end up here with -4 being equal to the log of our base to acid ratio. What's that ratio going to be like then? Again, the ratio must be 10 raised to the power of -4. So instead of having 10,000 times more base, we'll have 10,000 times more acid. So here, what form predominates when the pH is lower than the pKa? The acid will be favored because if we remember from our trick earlier, there are too many positive charges for an equal amount of acid and base to exist. So the takeaway here is really twofold. First, we have to understand that the Henderson-Hasselbalch equation can tell us what form of a functional group predominates at any given pH, but I think the most important point here is really just to understand why it is that when the pH is greater than the pKa, the base form predominates and vice versa. It's finally time for a payoff. We figured out the base to acid ratios of glycines to functional groups at a pH of 6. It's time to see which of the 3 ionizable states of glycine is going to predominate at that same pH. Let's consider our findings for the carboxyl group first. At a pH of 6, we said that there should be 10,000 times more molecules with the basic form of the carboxyl group than with the acidic form. Let's look now at our 3 glycine forms to see what that means. Which of these contains the carboxyl group? Only glycinium cation has the COOH group. The 2 other ionizable states have the carboxylate ions. This means that a ratio of glycinium cation to both glycine and glycinate anion should be 1 to 10,000. So we should have 10,000 times more of the middle and right molecule than of the left one. Why is this not enough information to answer the question prompt? Even though we have one ratio figured out, we don't know what the ratio of glycine to glycinate ion is. We only know that those two together should be 10,000 times more present than the glycinium cation. In order to get our final ratio for glycine's 3 ionizable states, we need to supplement our carboxyl group findings with those of the amino group findings. So let's do just that. At a pH of 6, there is 10,000 times more acid than base for this group. If we look at glycine's ionizable states, the glycinium cation and glycine both have the ammonium group, so the acidic form, while only the glycinate anion carries the amine group. Based on the base to acid ratio of the amino group only, we know we must have 10,000 more glycine and glycinium cations than glycinate anions. In other words, we should have 10,000 more molecules with the purple circle compared to molecules carrying the light blue circles. Now let's answer the prompt question. In what proportions do glycine's 3 ionizable states exist at a pH of 6? Putting these two basic to acid ratios together, the only ratio that can work for glycine's 3 ionizable states is 1 to 10,000 to 1. This allows us best to satisfy the two conditions we have. We must have 10,000 times more light blue boxes than purple boxes, and 10,000 times more purple circles, the ammonium groups, than light blue circles, the amine groups. Another way to look at this is that this is the only way we can have 10,000 times more glycine and anions than cations, and 10,000 times more cations and glycine than anions. If you need to make sure this makes sense to you, feel free to pause this video and look at the ratios, the functional groups, and the glycine states slightly longer. So it's interesting here. Let's tie this back to one of the earlier questions I asked you during this lesson. We said that when the pH of a solution is equal to the pI of an amino acid, that amino acid exists in neutral form, also called the Zwitter ion form. And here, we were able to show this simply by using the pKa's of glycine's functional groups. And also we showed that technically, you don't just have the Zwitter ion form of the amino acid. It's just that it's the form that's overwhelmingly present in the solution at that particular pH. And the last thing I want to draw your attention to is this. Do you notice the purple to light blue gradient that's forming as we move from left to right? For both groups, purple indicates the acidic, so the protonated form, and the light blue indicates the basic, so the deprotonated form. It's almost as if we can see the pH gradient building with the colors. So let's draw it here. We can clearly see that at a pH of 6, the Zwitter ion form predominates. But at a super low pH, it's the cation form that predominates because you have an excess of protons. And then at a super basic pH, the anion form predominates. And you can also imagine what would happen at an intermediate pH, say right here, you would have a decent amount of both glycinium cations and of Zwitter ions. This relates very nicely to our little trick from earlier on. We can clearly see that when the pH is lower than the pI, there are too many positive charges in the solution for neutrality. Now that we're pK pros, this next problem should be uber easy because we've already dealt with a bunch of pKs with glycine. Let's see what we're asked to do here. We want to see what charges glutamic acid and lysine will carry at a pH of 6. Why don't we need to tackle these very different amino acids separately? The pKs for all our carboxyl groups are in pretty much the same range, and so are those for the amino groups. So what's the difference then between these two amino acids? Well, one of them carries an extra carboxyl group in its side chain, while the other one carries an extra amino group in its side chain. And that's why these two amino acids have totally different properties. So let's look at all our carboxyl groups. Based on our previous discussions, what forms of all carboxyl groups should predominate at a pH of 6? That 2 to 4 range is much below 6, and so the basic form will predominate for all carboxyl groups. Same deal but opposite with the amino groups, if you will. If we look at their pKa range, it's pretty much between 9 to 10.5. So we know here the acidic form is going to predominate. How do we go about finding each amino acid's overall charge? The idea is just to look at the charges carried by each individual functional groups on an amino acid and then add up these individual charges. So looking at glutamic acid, we have 2 negative charges, the carboxylated anions, and then 1 positive charge, which adds up to a net charge of -1. Same deal but opposite again with lysine. Its 3 functional groups have 2 positive charges and 1 negative, adding up to a net charge of +1. So we see here how quickly we can determine the overall charge of an amino acid at a given pH as long as we're given its functional group's pKs. As a reminder, at neutral pH, acidic amino acids will always carry a net negative charge, and basic amino acids, which you have 3 of, a positive charge. Let's bring this all together with our final question prompt. We've loaded our lysine, our glutamate, and our glycine onto the middle of the gel, after which we power the whole thing by applying a 220 voltage difference. What direction is lysine going to move in and why? It has that positive charge, so it's a cation. Because cations go toward the cathode and our cathode is at the left, it's going to move left. Glutamate is an anion at a pH of 6. Anions move towards the anode, so it's going to move right. Glycine has no charge, so it's going to stay right where it landed on the gel. And there we have it. Lysine is going to occupy spot 1, glycine spot 2, and glutamic acid spot 3. To recap here, we described how the pH affects the base-to-acid ratio of a functional group, and we've also been able to determine the net charge of an amino acid at any given pH. If any of that made sense to you, or if the relationships are now crystal clear, that's really fantastic. But just take the time to plain memorize those amino acids so that you can apply all these cool relationships onto them.